You're going from which country to which country?
I'm flying to Chile.
Ah.
Right. I will be working on graph. And actually, set theory and graph, more like set theory, theoretical stuff than graph stuff. And I hope that it will be funny, at least. Right. Actually, there is something that I was saying that maybe it is not interesting for this group, but anyway, there is something called. I was looking to a paper called the semantics of graph programs. If you want to take a look, it's something related to, to functional programming, actually. But there is the title. It is in archive.
Ah, graph programs.
Right. It's a kind of specific and experimental stuff to deal with specific problems related to graph. Like a hot language. Something like that.
Interesting.
I would like to ask you, maybe I would be interested about proving the existence of graph with some properties, but for which the cardinality of its elements it's between some cardinals. I was thinking about that. Maybe it could be at the end of the day is about looking for models, right? Do you think that it could be useful to look at the semantical approach related to programs or something like that?
You mean the treating the graph as a program somehow, or?
Right. If you, it's like you describe a language, a higher language for dealing with graph, and you can define types. It's like translating graph properties and graph operation into types. Right?
Yeah, you could formalize reasoning about graphs. As long as you don't actually try to construct a graph that isn't finite, I think you're okay. But you could describe the properties of graph that is too large to be finite.
Right. But okay. Don't worry. The point is that dealing with infinite graphs, actually not countable a graph. That could be some way, right? To have a discrete object, but with an uncountable number of elements in its structure. But it exists. But actually, you can perform infinite computations actually with just finite resources. It is possible. It is not always impossible.
I still haven't read that paper that you pointed us to.
Okay.
But yes, that
What's the basic idea? How does that work? How do you perform an infinite computation?
Right.
Do you do it by reasoning and figure out that it's got to be the same thing or something?
It's something related to topology, actually. It's like you can describe infinite stuff if the topological description is not too complex, right? It exists a kind of hierarchy about the
Hmm.
complexity of things that you can compute. And then some infinite computations are not too complete, too complex to be performed, right? That there's a blog called seemingly impossible functional programs. And
Hmm.
it is talking about this stuff, seemingly impossible functional programs. And there is a presentation called the topology of seemingly impossible functional programs, actually, from a guy called Martin Escardó. He was talking in the last homotopy theory electronic seminars or summer school, something like that. Do we have Sergey here with us?
Not in person, sounds like.
Right, in the comments, he said he would arrive late and be with us briefly, so.
Yes, hello. It's just that I need to take care of my kid this evening. So if my kid isn't doing too much stuff that requires immediate attention, then for example, right now I need to wash her hands, like right now.
Okay.
But I will join in about 5 minutes. We'll see
Okay.
how it goes.
All right,
Great,
we'll see you soon.
Yeah.
right, good luck.
Well, it's quite a short paper I see, but I still can't, I would not attempt to summarize it.
Me neither, actually. I have to read it. I found it some minutes ago, let's say.
Hmm.
It looks interesting. I once wrote a little bit of code to analyze graphs just as far as to find out how many connected components they had. And that was in C. So anything one could do at a higher level sounds appealing from that point of view. Anyway, so I'm curious. I might look at it, but it is a bit of a digression. Thanks.
Right, and so I guess my question would be, is this a graph programming language, or is it a graph programming library that could be ported to other languages? If it is not a conservative extension over normal programming languages, what is it? Anyway.
I am not able to answer this question right now. But it's a good question, actually, right? What that?
It doesn't look like a library to me. It looks like something more of a departure from sort of what I would assume a graph programming would look like. It looks like sort of a new approach somehow.
Right. It looks like a library, so maybe trying to construct something from a host language. Okay. It is actually you can I believe that it has an entry in Wikipedia. Possible. So graph that data. No, maybe not. Okay, anyway. Abstract.
The graph programming. I don't know.
I don't find that. I am wrong. There is no entry in Wikipedia for that. I was confused with the entry in Wikipedia for abstract semantics graph. Is an like of a generalization of semantic trees. Something different. I was wrong. Right. It was the paper just.
Right, it looks as if there might be two other programming languages also named GP. So that's a little confusing.
Hello. Is the sound okay? Should I do something to
Sound
get
good?
rid of it?
All right.
That's good. Okay. Because
It's a little muffled.
Okay, a little muffled.
But if you're
Um,
facing the camera, it sounds a little better.
Yeah. Well, I don't know what's best. Probably switch off one of the audios. What about now? Is it better?
Oh, except for getting an echo.
Right.
Oh, you're getting an echo. Okay, that's not good. That's not good. It's not good. All right, then it will be like this. All right. Sorry, I didn't want to interrupt whatever you were discussing.
I believe that we are done with our previous discussion.
I have one quick question on the filter chapter or section. Seems like you define your type class with two methods, filter and with filter, that seem to do the same thing. One's defined in terms of the other. Why have both?
This is just a Scala syntax. So in Scala, you're supposed to define a function with named with filter for different reasons. If you define that function on a class, then you can use you can use the syntax where you have for yield, and inside the for yield you write if.
Oh, and it calls with filter instead of filter or something.
It's hardwired to call with filter.
Okay, so it's one of those monadic things where you don't have to inherit from monad, you just have the operations.
So
with the right
if you,
names.
you don't have to, it actually doesn't, the for yield doesn't have anything to do with monads per se. It's really for any functor that has certain methods, that then you can use certain syntax. It's a purely syntactic device. So for example,
but it kind of models monads in a way, you know, because
you see, suppose you have
it doesn't have to be.
No, suppose that you have a block where you have only one left arrow, right?
Yeah.
Let me maybe.
And the yield.
Yeah, so you can still write a for yield for this. Maybe let me share my screen. For now, let me just share my screen. Okay. So for example, you can write for, and then x going to list of 1, 2, 3. If x greater than 1, yield x. Right. So this is translated into list 1, 2, 3 with filter x going to x greater than 1. Dot map. Well, let's call this. Let's make it a little less tautological. Let's look at like this. Right.
Okay. And why wouldn't they just use filter?
Well, it's just a syntactic convention.
Okay.
So
All right.
they could have called it filter. They decided to call it with filter. So,
But they didn't call it with map.
no, they didn't call it with map. That's right. Yeah. So they could have called it something else, but they chose this name. So, and this is built into the compiler, right? So this syntax,
I figured it was something like that.
Yeah. So I guess they wanted to make it something that you wouldn't define by chance. Maybe.
Yeah.
So in any case, but it's the same as filter. So the thing is, then you have this code automatically generated out of this. Right? It's just a syntax device. So if you write this syntax, the result is as if you wrote this code. Now notice here, there is no flat map in this code. There's no flat map in this code.
There's only one left arrow.
That's right. There's only one left arrow, and it's not necessary to have a flat map. And so this doesn't use the fact that there is a flat map on the list class. So you can have a different class that doesn't have a flat map. It just has a map and with filter, and you will still be able to write code like this.
Okay.
Even though it's not a monad, let's say.
Yeah.
Yeah.
Yeah. So let's suppose I have my list, whatever that is. It's my list. I don't know. It may not be a monad. It may be something else. But it has these methods with filter and map. So then that's sufficient. So that's why I don't like the. So that's why I don't think it's necessary to think about monads when you talk about the syntax. So for yield, I call it just functor block syntax.
But you can use a functor block with monads. In fact, you usually do.
Yeah. Well, yeah, you usually do, but you don't have to.
I see.
And
okay.
There's nothing special about this syntax other than if you have more than 2 arrows, you need flat map. If you don't have more than 2 arrows, you don't. If you have an if construction, then you need a filter operation. If you don't have an if construction, then you don't need a filter operation. So then I ask, what is the type class that allows you to write this kind of code where you have only 1 arrow and 1 or more if operations? And that's the filterable.
I see.
And then the laws of the filter operation come out of the requirements of this if. You know, what a programmer would think this if should be doing. So for example, if you have 2 different conditions, then it's the same as if you had a single condition with a conjunction of all the conditions.
Yeah,
That-
if there's
that's kind-
nothing in between, I guess. Yeah,
Well, there
So,
cannot be
actu-
anything in between.
there could be a
Sorry?
regular assignment, right?
There can be an assignment, yes. Correct. If that's correct.
Okay. So one thing, talking about Scala names and things like that, in the extension methods, all your things end with syntax, something syntax to define the extension
Yeah.
method. Is that syntax word, is that special to Scala, or is that just your convention?
No. This is just for convenience, so that you kind of remember that this class is just for syntax purposes.
Okay.
And
Okay.
in Scala 3,
Good.
it is not necessary to do quite so much boilerplate. They made a special keyword extension to make extension methods.
Oh, good. All right. I'll have to look at that.
So you don't have to dance around quite so much and import all those classes, with names. In Scala 2, you need to put a name on each of these classes. So extension method requires you to define a class, which will be a JVM class, and it needs a name.
Like something syntax.
Well, so
Yeah.
so some people use different conventions. It doesn't have to be syntax. It's just that if you have an implicit, essentially it's an implicit conversion to a class in a value, and then that class has the method. So you can define, in this way, you can pretend that the method was defined on some other type or some other class.
Right. Which can be useful. I get that. Yeah.
All right. Now, wait. Okay. Right. So this is a new kind of functor. Anyway, so you had
What's
any
your
other
daughter's name?
questions? Sorry?
What's your daughter's name? I want to say hi.
Oh, Ines is her name.
Hi, Ines. Hi.
Hi, Ines.
Hello. So anyway, I will stop sharing because she's just drawing.
All right. I did have another question, but if somebody else wants to jump in, that's fine. In what was it? Example 9143. Let's see, do I have that?
What is that example?
It's the one that has, let's see if I can share this. Where's preview?
Sequence of requests.
Oh yeah, it's over here now. This example, first of all, it uses take while, which doesn't seem like a real filter to me, right? Usually I was thinking of the filter is more like something that works on each thing independently. So if you have a list and you say, you're iterating through the list and you say, if something, I expect it to keep or drop depending on what that key is, and not suddenly start dropping the rest of the list because it happens to be true or something like that. You know what I'm saying? So it
yeah,
seemed,
well, why didn't you? Why?
Sorry, say again.
Well, so your expectation was that a filter will not remember what happened to other elements when
That's right.
when doing its job, right? That's what you expected, right?
Right.
Okay, but why not? So I mean, I don't have a good argument for or against it. I just don't see what law prevents me from doing it.
Yeah, I was thinking about that. How would I write a law that would capture that? And I don't know. I'm just sort of saying
so for example,
it's my
we still
intuition
have
of what I thought, and if, what a filter would do. It seems like it would be a different thing if it had memory,
Yeah, well, it's a very limited kind of memory, right? It's limited to the information about whether it was successfully filtering or not, right? So it does not have any information about the values it's filtering, other than whether some value was successfully passed or failed. So naturality laws still hold. You still don't look at the types or data that you're filtering. You don't know what types those are. You don't know what data that is. So I don't know what law would prevent you from having this behavior.
Well,
actually,
Could you, if you wanted such a law, could you phrase it in such a way that if your filtering function returns true, then if you filter again on the result of the first filter and you have another filtering function that returns false, it does something.
I was kind of thinking.
I don't know. So this is not easy to do that. So actually, it's not easy to get like laws like this. So in any case, to me, it's useful to say that filter could be any kind of those operations like take while or drop while or whatever. So those operations. So I had the following picture in my mind. So in all these different type classes, like functor, filterable, and monad, and so on, essentially, they replace loops with some operations that hide the looping from the programmer, right? So, for example, the map on the sequence hides the loop. It looks like just one function call. Filter hides the loop, and flat map flattens two loops into one. Two nested loops into one non-nested loop, and all of this is done without writing loops explicitly. So if you write a while loop which repeats until a condition is met, or while a condition remains true, that kind of loop is replaced by a filterable operation. So if you like write a loop that, take while, and it turns out that all the laws that filter operation has also apply to take while. And so if you figure out some law that you would like to have that prevents take while from dropping everything, I would be interested to hear it, but I don't know how to do it.
I think Peter raises an interesting point that generally a filter is not sequential, right? You could do it in parallel, but take while seems to be essentially sequential, because, you know, if I say take while, you know, the number is less than 10, but there might be a number way down in the list that's also less than 10, right? And so, but you
Yeah.
stop at the first instance where it's no longer 10. And so
Yeah.
there is that dependency with the take while, whereas the regular filter in general does not have that kind of dependency. You could do it all in parallel and then, you know, remove all the ones that are false. So I think there's something inherently sequential about take while and drop while and its ilk, I think.
Now, what about trees? What if you filter a tree? Not a
Yeah,
list.
I was just thinking that also because if we want to talk about operations which are sort of like traversing, then ideally we want to be able to do them on trees as well as on lists.
Yeah,
And if you
yeah,
drop,
graph.
drop something
You know,
from
you're
a
filtering a
tree,
graph. You're removing nodes from a graph that don't satisfy some condition, right?
yeah, and if you remove something, that you may also remove its children, right? Its children would have to go as well.
Right. You remove all children after that node, right? But you could do this in parallel. Hello?
Well,
Right?
you can't really do it in parallel if your condition says if this condition is false on the left side of the graph, then I want to stop doing things on the right side of the graph, right? If you're trying to do it in parallel,
Yeah.
like doing each side in parallel, then it's not going to
That's
jump
true.
over. It can only do
But
it
I don't know if that's
continuing to
actually
go down.
Yeah, I don't know if it satisfies the laws to do that kind of thing. But it's anyway. I just wanted to say
Okay.
in this chapter, I don't think I have a tree as an example of filterable, which is a pity. I don't think I have an example of a filterable tree, because filterable trees are not so easy, right? So usual trees are similar to non-empty list. They cannot be empty, but the filterable operation, the filterable collection needs to become empty sometimes, right? So
That's right.
because sometimes you filter out everything, and so the result must be an empty collection. So any kind of data structure that is always non-empty cannot be filterable.
Can we define a notion of an empty tree?
Well,
so you have
That
to
has-
change the definition of a tree to include something like an empty tree. Yeah.
Right.
So
Yeah.
easiest thing would be to just
And-
say it's either empty
No.
tree or a usual non-empty binary tree.
Right. And you need a different kind of a notion of what it means to delete something, because with a single list, we just compact it, right? But with a
Yes.
tree, when you delete an intermediate node, do we really want to delete the whole subtree, or do we want to remove that, but then all the children nodes become the children of the parent of that deleted node, for example, right? So there are
Okay.
different options on how to define
That's right.
those.
Yeah.
Because of the two-dimensional, the hierarchical nature of it, it becomes a little more
Yes.
complicated. Yeah.
That's right. So there's not a clear way of defining it in the best way, right? So we might define it in a greedy way, say that, you know, if something is, you could even define it on a list in this way. If at least, you know, it's a filter that says for all, you know, it's a for all function in Scala. It's also a filter. But if just one doesn't satisfy, then the result is an empty list. You just you throw out everything if at least one doesn't satisfy. So you could do that on a tree as well, or you could say I just delete the leaves that are not passing the condition, and then I graft all the rest of the tree back to that place, one level up. Since now I have one level free, since I have removed the leaf, so now I have a free level. So I just collapse that level, move the remaining tree one level up, and continue. So this is kind of a minimum operation. I don't lose any data that passes the test. I just remove the data that doesn't pass the test, right? So
Sort of another way to do that. Another way to
Right.
do that is like on tree, you could have like, you know, the different traversals, pre-order, post-order, in order, whatever.
Yeah.
Those yield like an iterable. And then on the iterable, you can use filter, throw out stuff. And then you'd have to have like a builder to rebuild the tree on the others, the other end.
Yeah, but if so.
But
so
maybe you
or
don't
could
want to
say,
go into another tree in that case. But anyway,
well, maybe you don't want to change
Maybe you
the
do.
order. Maybe you don't
Right.
want to change the order of the tree. You just want to delete some subtrees. Right? Or you can say if a subtree contains a leaf that fails the test, then anything below that level is just omitted. You could do that, or you could do something else. So in any case, this is the question is how to define this operation so that the laws hold. And sometimes so that's the only guiding principle. Actually, this is an important part. You need to check that the laws hold, because otherwise you're defining some kind of operation that might make sense. But I gave examples in the chapter of filter operations where the laws do not hold, where you would think it makes sense to filter like that, but actually the laws don't hold, which means that if you compose two filters, the result is going to be unexpected. Finally, it's all a question of what is good for your application, what is necessary for your business logic. So is this kind of filtering helpful for your business logic or not? And if it is, then even if the laws don't hold, it's not important, because, well, maybe your business logic does not correspond to composing filters. So you only have ever one filter applied to your data, and you never compose any filters because your business logic doesn't support that notion. And if you never compose any filters, then the composition law is moot. You don't care if it holds. And so then you might also use a filter that violates that law, for example. Anyway, that's so yeah. So I think I'm thinking of adding at least some examples or exercises where I show how to filter a tree, because it's really a pity, because it's an interesting example. Like, for example, non-empty list is not filterable, but ordinary list is filterable, right? Ordinary list is just 1 plus non-empty list. And similarly, ordinary binary tree is not filterable because it's never empty. But 1 plus ordinary binary tree is filterable. And so that kind of example might be illuminating.
Looks like Hugh might want to say something. He's got his hand up.
Oh yeah. I was just Adrian mentioned the idea of doing more than one filter operation, and I was wondering, should it be part of the intuition of filtering that it's idempotent? Because, like, for me, when I think of filtering examples, it is. And if possible, is that something that we could derive from other laws, or?
You can derive it from the composition law, right? Because it's supposed to be that if you apply P and then if you apply a filter and then apply another filter, it's the same as applying it as if you're applying one, but it's the conjunction of the two things, right? And if the two things are the same, it just reduces to one. I had the same question. That's
Is
why.
that a law?
'Cause
Ah,
I-
okay, cool. I think I must have missed that discussion, but
Yeah.
no, that sounds good.
Yeah.
Thank you.
No, I didn't
The
say it
laws
before,
come
but
to
I-
your rescue.
Yeah.
All right,
Yes.
maybe I'll drop off now. You can continue. So my daughter seems to have little interest in doing something. All right, I'll talk later.
Okay. See
All
you
right.
soon. So if no one else has any questions right now, I have something for show and tell. Which
Okay.
okay, and I will share my screen.
Should we say hi to the new people?
Yeah, we should say hi to the new people first. Let's see. I guess.
Hello.
Hi.
Yes.
Hi, my name is Rajkumar. I joined a little late today. I got actually science of functional programming from LeanPub, but I never started learning it, and I just got to know this meetup exists and would like to join and learn functional programming.
Well, welcome. Right. So this is not just functional programming, but how to reason about the kinds of things that you find in functional programs. So it's yeah, it's not too basic.
Okay.
Yeah. So Aaron, do you want to introduce yourself?
Hi, I'm a bit sick still. It's been a couple weeks now, but so I didn't join at the right time because I keep napping. But anyway, so I thought maybe this presentation would be a little bit easier than some of your other ones since it's Scala and I know a little Scala. So I thought maybe I'd get a little more out of it. I'm afraid your presentations are a little bit intimidating, very mathematical oriented at times and somewhat abstract. But anyway, this one I thought would be a little more accessible since I know what functors are fairly well and filter and map and so on. All right.
Okay, well, good to have you aboard. So yeah, so I was going to present, Antonio.
Right, maybe we could tell them that we have the Slack channel and if they are interested in joining.
Right, so we have a channel on slack.com. And if you want an invite, I guess you can send me a message through Meetup with your email, and then I can invite you to Slack if you have questions you want to ask offline.
Yeah, sure. I will add my email. Yeah.
Okay.
So is it in today's event or I should add it in the whole group? SF types, theorems and programming languages.
If you can send it to me as a direct message on Meetup, that is the most convenient for me.
Okay, yeah, sure.
Right. Okay. Okay, so anyway, this here we go. I did a little, can people see that?
Right. We see your ACDA code.
Okay. Yeah, so I did my very first experiment. Is that still visible?
Right.
Okay.
As long as I make my window bigger, yeah.
Looks good here.
Yeah,
Is this
that looks good.
Okay, so yes, this is my first experiment with Agda instances, which are Agda's version of type classes. And so I was trying to express some of the stuff in this chapter. Ran into some interesting interesting things. So what I wanted to do was to express filterable as two pieces, one of which just has the implementation of filter in it, and another which has the implementation or the specification of the laws. So this version of filterable expresses the laws as Sergey's initial set of laws, and then later on he has another set of laws expressed in terms of filt op. And I didn't get far enough to try to create another type class that reflects that. I didn't bother to specify the laws for functor, which is probably something that you would want to do in a real implementation. This syntax seems to mean that functor becomes available as a thing for which you can make a type class instance, which you do with this syntax. So what I'm saying is that filterable one depends on an implementation of functor for F and quasi-filterable for F. And opening these records is supposed to make it possible to just access the fields and have Agda figure out exactly where the fields come from and to which instance of the type class it applies. But that doesn't seem to quite work, because I find that in each of these expressions I have to spell out both the module from which the function comes and the instance to which it applies. I only have to do that once, and then Agda is able to figure out the rest of them. But it is a little bit puzzling why you would need to do that.
Yeah.
So aside from
But
that,
you're saying the F map earlier in that same definition, that it didn't require you to qualify that one.
It doesn't. I didn't do an experiment to see whether I can spell it out fully on any of these, and then it will find all of the rest. So maybe I could try doing it on the first one instead of the last one. I spelled it out fully on the last one because that was where the error messages were all pointing. But maybe any one of them will be enough to yeah, that seems to make it happy. So I guess
still, why do you have to say it at all? Yeah.
Yeah, as long as you pin down one of the occurrences of one of these functions that you're using, that is maybe enough to resolve all of the meta variables that Agda generates. But the error message that you get for leaving these things out is really quite voluminous, because Agda has generated a very large number of meta variables, and once it can't solve for any of them, it doesn't seem to be, once it can't solve for one of them, it doesn't seem to be able to solve for any of them. And so it gives you this long list of errors when you leave this out. But beyond the Agda mechanics here, there's also some interesting things about functor itself. So what you would like to do in functor, probably in general, is to say that fmap is implemented in terms of filt opt. So you would actually have a definition of filtopt here, and then you would have fmap as a subsidiary function defined in terms of filtopt, which is a thing that you're allowed to do in an Ogda record. But filtopt itself is defined in terms of psi and deflate, and psi is defined in terms of I'm sorry, I'm doing this on the wrong functor. So yeah, I mean, filtopt would go here in quasi-filterable. So, but yeah, I was saying psi is defined in terms of filter itself. That is specifically the filter on option. So, so I'm not sure I can define things quite the same way that Sergey did in the book. I'm not sure whether that would result in a circular reference. I didn't quite work that out. But right, the filter on options seems to be maybe a little more primitive than the other sorts of filters. So I think you would need to express that. The other interesting thing to me here is that filter, depending on how you implement it, either filter could be primitive or filtopt could be primitive. And the Ogda way of doing this as a record doesn't seem to be quite ideal for capturing that, because I think you have to pin down what is concrete and what is abstract. And in the general case, you would want either one of them to be abstract and then do some sort of mix in to get the concrete one. And I'm not quite sure that Ogda is set up to do that.
You could define it in the record, right? Because that's just defining the type. It's more like when you create the instance, you'd have to do one and then define the other in terms of the first.
Right. So my question.
Yeah, I don't know if there's a mix-in kind of thing.
Yeah. Can I define? Is there a tidy way to define the instances without typing out the definitions of both fields? Can I? Yeah, I have to think about it some more, but it seems to me that
I mean, at least you could define the two functions that go from filter to filter op and filter op to filter. And then when you create the instance, you define one, and then you just use the function to define the other. But still, that's a little more work than you want to do.
Right. You would like to have that done. Once you choose which one you want, you would like to be, you'd like it to be relatively automatic to bring in the other. And
you basically want inheritance.
Yeah, that might be easier if these were modules rather than records. But I'm not sure whether the Ogda instance mechanism works on modules in general. In particular, this syntax is only mentioned in the Ogda documentation for records and not for modules. And so I don't, I haven't done the experiments to try to figure out how you could do that, if you can do that. But it does seem to me that a lot of the Ogda documentation is sort of left as an exercise for the reader. Whenever you want to do anything that is not pretty much the same as in every other dependently typed language. Once you get to the really Ogda-y parts of Ogda, it's you're a little bit on your own. So anyway, that was my Ogda adventure.
But still, even if you can't sort of smoothly pass between different expressions of the filterable concept. Just having one implemented is pretty cool because, as I understand Agda, you can then define it for, let's say, the list functor, and it will be guaranteed to be a lawful instance.
Right, as long as you implement all of these laws here. I mean, these are the specifications of the laws, but the actual proof of the laws would have to be on a per filterable basis. So
I would be curious to see how that works, and like the first example of applying that to an actual functor.
yes, so would I. But I didn't get that far. Perhaps that is my homework for next week.
This is great because at least I have actually seen and partially understood some Agda code, which is a first for me. So thank you.
Yes, and I also partially understand it. So yes, very exciting.
Do you have in here a case where you create an instance of one of these?
No, I have not gotten that far. But yes, that would be a good next step. So yeah, so maybe I should do that for next time, or attempt to do it for next time, and maybe have a report on my failures.
Yeah.
So
I did do some of that about not finding it, but yeah. Huh.
right, but filter seems to be like a particularly good test of the idea of how you would do type classes in a language, because there seem to be more possible ways of implementing filter and more possible ways of expressing the laws than there are for some of the simpler constructs that we've seen so far. So
I wonder, just real quickly, if you had done in your Agda code, instead of that open with the double curly brackets, if you just said open thing public, whether that would have done it.
Yeah, let me go back. I think that will make, so if you open functor blah 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 blah, I think that makes functor.fmap visible. But I think it doesn't let you do this and say that functor f is an implementation of functor, and which is, I think, the thing that lets you do this fmap without saying functor.fmap functor f. It's not clear from the Agda documentation exactly which bits of magic are associated with which piece of syntax. So I'm just following their very limited examples as best I can. So I don't know if there's a
Adrian?
Yeah, the thing you might try is adding a constructor field to your record.
Hi. In your example, you use set functions, right? Like f is a set to set. What happens if you use list instead of set there? Is the default definition of list satisfying? And then the next question, of course, is what if you try and do like a tree? What operations are required in order for this to work?
Right. So set has nothing to do with the Scala notion of set. This is how Agda says it's a type.
Oh, so set just means type?
Right. So it has nothing to do with a data structure. It is a universe that contains types.
Okay.
So right. So this is saying that f is a type constructor in the sense that we usually talk about type constructors in Scala or Haskell. It takes
Okay.
whole arguments in terms of type.
So then
And,
does Agda have a notion of a set, a regular set?
not there might be somewhere in the Agda standard library.
Okay,
Probably.
But
okay.
yeah.
In that case, yeah, my original observation was that I was thinking was irregular sets, but okay.
Right. So you might also be curious about where set one comes from. So the universes of types in Agda are stratified, and because functor mentions set, functor itself has to live in a universe that is big enough to contain set. So you have to go to the next level up, which is set one. So,
Right.
So yeah, any other questions or comments on this particular fiasco?
No, it's good.
Okay. So yeah, it's great to be able to talk in sort of general terms about how a dependently typed language would let you prove all these laws and say all this stuff in a more rigorous way, but actually the mechanics of it turn out to be, I guess, as troublesome as writing a real program in any other language. It's great to say, oh, you can do this, you can do that, but then actually doing it usually involves pulling through the documentation if you're not super familiar with the language, and trying a bunch of different ways to do things, and so.
Yeah. And that wasn't even getting to the point of proving any laws or anything, which
no, yeah, there's
is
no,
even a whole nother level of complexity.
right.
Because often it seems like it should be easy, and then it just isn't, because some fact that you learned in high school just isn't apparent. It's not, something like commutativity of something, oh,
Right,
of course that's
yeah.
the same, or associativity, of course it's the same. And then
Yes.
you go, oh, but now I have to prove it.
Right, A plus B equals B plus A, but it's a whole digression to have to actually convince Agda of that.
Or find the appropriate theorem somewhere, but yeah, go ahead.
Are you telling me that the definition of the what you defined in Agda will not allow me to define a filterable function and then just say, my function P is a filterable, and then to have the compiler type check? You're saying that that's not doable?
Well, if you want it to be lawful, so for example, if you want to say that list is a filterable, you can definitely define the filter function that operates on a list. But if you want to do it in a lawful way, then you have to go down and actually implement each of these four laws here. You have to provide a proof of naturality, identity, composition, and partial function before you can convince Agda that your filterable really is lawful.
Oh, so the proof has to be provided. This definition of a filterable one does not check that the function that you said is filterable, the data structure you said is filterable actually is. It doesn't check these laws in any automatic sense. Okay.
Right. I don't, yeah, it's probably not in general automatable to derive the proofs for these laws.
I think maybe in Sergey's chapter, he used like Scala check or something like that to sort of generate a bunch of cases and check laws and things like that. But yeah, anytime you have these things that are sort of universally quantified, you can't just check them because you can't check the infinite number of cases. So the best thing you can do is kind of go through the space and generate cases and see if you find one that's wrong. But in this case, where you prove things, then you can prove things about, you know, infinite sets, basically. And so you can prove that these things are true,
Right.
for your data structure, and it's
So,
filter operation.
so yes, a better example would actually include proofs of these assertions. So yes, for next time, maybe I can try to come up with an instance of this for list or something like that.
Mm-hmm.
So I guess one other thing to say is that for some data types, or for some type classes, I guess, it is possible to derive instances automatically. So I think for FMAP, you can typically derive FMAP automatically given a data type definition. So in that case, maybe you can also derive the proofs of the laws if you have a suitable mechanism for doing the automatic derivation. But that is way beyond the scope of my knowledge of Agda or any other programming language.
I don't know Haskell that well, but I'm pretty sure you can say like derive FMAP and derive various things, and it will figure out how to do it, I guess, based on the structure of the type.
Yes, but I think there is something that there's some kind of magic switch you can provide to tell it which type classes to be able to derive instances automatically for and how to do that. And that it's sort of like I guess a type aware macro that you have to write, which I assume is going to be pretty complicated because it needs to traipse through the structure of your data type declaration. So yeah, that's a thing I don't know about. So any more of this, or should we go back to the book?
I guess that's enough of that.
So yes, we were at section 9 dot something. How far had we got?
Well, I was talking about 9.1.4.3, but we could go on to the what is the next section anyway?
The exercises, 9.1.5. So Confucius gave a wisdom on each of the 7 days of a week. Sometimes the wise proverbs were hard to remember. Confucius forgets what he said on a given day. He also forgets on what he said on all the previous days. And I think, yes, in fact, that is described by a filterable functor, because it's the same case as the server example on the previous page, except that the sequence is reversed.
So I think that's why maybe it's not, right? I was thinking that it had to be more like it's going through and it's looking at the answers you get. And then if it gets like a no, then it can continue to drop stuff. But as long as it's getting yeses, it has to keep those things in there,
Right.
right?
That's sort of
Because otherwise the identity law wouldn't hold, right? As long as it's getting yeses, if they're all yeses, then it has to be the identity. So you can't drop things as long as it's all yeses.
exactly. But apparently you can drop whatever you like if there is at least one no. So
But probably only from then on.
I
Well, we don't know for sure.
I
Okay.
don't think there is anything in the laws that talks about the order of the calls to filter. And so, assuming that that's the case, then if you get any false returns from the filtering function, you should be able to drop whatever you want.
Okay. And the laws wouldn't prohibit it, I guess, is
Laws don't prohibit it.
the point.
Right. Now, if you want a law that says that you don't drop anything unless you get a false from filter, then yeah, then we have to figure out how to express that. But then neither one of those examples would follow that law.
What I remember Sergey saying was that the laws always allow you to drop more stuff.
Right. Yeah, I think
You
that's
can
true.
never drop less stuff than it seems like you should, but dropping extra stuff is generally safe from the point of view of the laws. And this is a very rough heuristic, of course, but I think he said
Right.
something like that.
He did
Right,
say
and the-
something like that.
And the limit, of course, is you drop everything and you have an empty list. Then that everything is satisfied.
Right, but you have
But
to
it
do
has
that.
to satisfy the identity law still, right? So
Yeah.
if it's universally true, it's got to just return the whole list.
Right, but if you get any falses at all, yes, then you are allowed to throw everything away.
Yeah, this is the exercise is kind of interesting because there's a certain kind of okay, maybe I'm interpreting it too critically, but if Confucius forgets what he said on a given day, he also forgets what he said on all the previous days, which means that what you're left with is there is no day in which he has forgotten, right? To the right. So you have to drop everything to the left of any day in which he forgets, right?
Yeah.
So it's not a take while where you run into the first day that he forgets and drop everything prior to it. You have to continue to the end of the list to make sure that there isn't some other day in the future where he forgets something.
Mhm.
Because if you did, then yeah, so there cannot be any days left where he forgets anything, basically.
I guess it's a reversed take while.
Yeah, I think so.
Kinda, yeah.
Reverse dot
That's
take
what Peter was
while.
saying. It goes in the opposite direction from the other thing, which is still which is fine, I think.
Yeah, it's kind of a maximal take, right? And that's the trick, is that because it's maximal, you don't know, you have to go through the whole list before you can tell whether the filter has, should be applied or not, right? So, yeah. Whereas normally take while, you stop at the first while it's true. So
Right.
interesting.
Well, as long as you reverse it first, then you can do a normal take while.
Yes, you're right. Yeah, if you start from the right side and then come forward. Yeah. Okay, that's interesting.
But there's nothing in the type class that says you can reverse a list or reverse whatever it is you have.
Yeah, there's an inherent sequentiality here that I think is interesting, right?
Mhm.
Yes.
Yeah. And
What-
from a functional language, the whole point of functional language is that we're supposed to be you know, able to evaluate in any order and so on. But for some reason, this kind of take while, does that mean the take while is inherently not functional
Well,
because of the sequentiality? Yeah.
there are lots of things that you can express functionally that are inherently sequential. Lots of computations that depend on the results of previous steps. So,
Fold.
yeah. So, I mean, there are also lots of computations that could in principle be done in parallel because you don't have such a dependency.
Yeah. But
But,
then fold is like filter, right? You can implement filter using a fold. So I think they're related in terms of the
Yeah.
dependency. Yeah. Interesting. Okay.
yeah. So, yes, if you have some sort of proof of commutativity, I guess, when you are operating over some set of elements, such that you can show that it's okay to operate in any order, then you can do your operations in parallel and merge at the end, I assume. So, but otherwise, yeah, you may have a sequential.
Yeah, I mean, I'm just thinking of it, but fold, you cannot apply associativity law when you're doing fold, right? Basically, fold says, I want to parenthesize from the right side to the left or something to that effect, right? You cannot just do an arbitrary grouping and then apply fold that way, or can we? I don't know. It's
Right. Well,
Well, there's often a fold left and a fold right, and then there's a fold, which assumes that your operation is associative. So it doesn't matter which way it goes.
so it doesn't matter.
But I don't know that it's doing it in parallel or anything like that. But I guess you have that option.
Yeah. Okay.
So
Right.
in the case of this example, sorry. Someone else. In the case of this example, I'm trying to figure out what the types are. So I guess there's one type which is a sequence of wise sayings, one for each day of the week.
Right. I guess sequence of proverb.
Proverb, and then that's the source type. The destination type is the collection of proverbs which he actually remembers.
Right. So I think it's list of proverb or sequence of proverb in both cases. And
Okay.
the input will always be a 7-element sequence. And the output will have somewhere between 0 and 7 elements.
I think it's generally assumed that the input functor and the output functor are the same. So whatever sequence you have going in, it's the same kind of sequence coming out.
Right.
Oh, are these all endofunctors?
Yeah. Well,
Did I miss that?
I mean,
I may have forgotten that.
in a programming language, they're all endofunctors because they're just
yes.
going from type to type, right? But wait, do you mean something, or maybe you mean something else?
Right. Is there a category that is specific to the filterable that you have in mind, as opposed to the general category where the types are the objects?
No, that makes sense, actually. I'm just looking back, and like the early examples they all seem to be endofunctors. I just hadn't that didn't sink in when I was reading it earlier. Okay,
So,
and function P is operating on the type of wise sayings.
Right.
It's a predicate on the
On the
set of
wisdom.
wise sayings, or possibly the combination of a wise saying and a day. I'm not sure about that. Anyway,
Right, the day doesn't actually seem to enter into it as long as the data structure you're filtering on is sequential.
if it has the sequence, you don't need the day.
Yeah.
Yeah.
Now, one thing to say is this only works if the sequence is finite, because we're the thing we really want to do is to reverse the sequence and operate on the reverse sequence. But if it's infinite, then you can't reverse it.
You have to keep looking for that one day where he's forgotten. And you might look forever.
Right, but you can do the same sort of thing if you're doing it in the forward direction. So the example about the server requests on the previous page, you could do it is reasonable to do a take while, even if there are infinitely many server requests.
As long as take while works
Yes,
lazily, basically.
yeah, I believe that is how you would implement it on the stream, is lazily. I think that's how Scala.
Yeah. What about the next one?
The next one, even filter. A value x:(t) is kept in the sequence if p of x equals true, and only if the initial sequence has an even total number of elements, for which p of y is false.
Shall I share just so someone can, so we can see?
Go ahead.
Yes.
Yeah, just in case.
So I think that is probably not lawful, because if there are 0 elements for which p of y equals false, then maybe, right, 0 is an even number. So you satisfy the identity law if there are no falses. So maybe that works.
Wait a minute. Does it satisfy the identity law if you have a sequence of length 3 and they're all true?
Yes, because there are 0.
Then when you
there are 0 falses, and so you're allowed to keep all of the elements.
oh,
If there's 1 false, then you have to throw everything out. But that's allowed because you had a false. That still satisfies the identity.
But if you have another false, then you have to keep everything again.
All
right.
You have to
Oh,
keep everything for which is true.
Oh,
Yeah. So then it behaves like what you would think of as a normal filter.
I see.
So I think
This lacks a monotonic property, which intuitively I would want my filters to have. So if I strengthen my filter, I would expect to get a smaller result.
Yes, so I think that's Pete's intuition. But that's a whole new law, and then of course you have to decide whether the original formulation of filter that didn't have that law is the one that gets to be called filterable,
Yes.
or whether you have to name it something else.
Well,
Okay,
doesn't
so
the
that's a
composition
digression.
law kind of say that though, right? If you strengthen it by adding another condition, then it should be the same as if you filtered by the first
Wow.
condition and then applied the second condition.
It does kind of look like that.
But the condition here though is on the whole list, right? There has to be an even number of P of Y equal to false. So that's the tricky
Right.
part. I don't think this is lawful. Something that depends on the totality before you can do a filtering requires at least, 2 scans, right? First time you have to
Yeah.
figure out whether there is even number of falses, and then you apply, if so, then you apply the filter.
I'm actually, and what the function P, sorry, Daniel, the function P can only look at one thing at a time, right? So it's the
That's right.
it's the result
but
of
right. But the
Let me
removal
chime in just for a second. So the point here is that you need to check the laws. So we don't know in advance how the function P is going to be used in the collection, right? So you can have a data type where you only have, say, 3 items of data at most. It could be a list of very small and size that is finite and known in advance. And so then the logic of this function could be that you actually check P of X on every available X first, and then decide something, and so on. You could do that. So you shouldn't think of only sequences when you think about filtering. So the whole point is that you want to be able to define filter on all kinds of data types. Not necessarily collections. So here's, for example, exercise 9153, right, which you're showing right now. And I give a couple of examples where there isn't obviously a filter, or maybe there is, so we need to check. Really. It's not obvious. So I do actually have a tree example. Which is kind of
Wait, quickly, what is the answer to 9152?
Yeah.
It is lawful.
Well, I don't remember.
Okay.
So I think it is lawful. Yeah, I think it is lawful.
But
so
somehow I wouldn't be too
actually,
surprised if it failed composition somehow.
No, so if you have an even total number of elements for which P is false, then probably, right, because you could have yeah, so I'm pretty sure that composition law would be violated by this. Because you first filter out something where you have an even total number, where you do not have an even total number, but that changes the number of things that you keep. And so then the next filter does not have an even total number, something like this. So anyway, I don't want to improvise right now, okay. But my intuition is that this will not be lawful. But this is not because you have to go over the entire sequence. It's because of this condition that the total number of elements for which P of Y is false must be even. And that's,
right.
You're not supposed to count those elements and depend on that count.
Yeah, usually we want like the filter of a list concatenated with the same filter on another list should be the same as the filter on the concatenation of the 2 lists, right? We expect that kind of, filter on 2 separate lists.
Certainly, so certainly that will be violated. Yeah.
Yes,
but this is a different.
But you can't
law.
prove that from
what
the
you're
laws.
saying, yeah, well, what you're saying, you're imposing a different law, which will only be available for lists, right? This other law might or might not be desirable, but certainly it appears reasonable to say that. I just think that you can find a simple example with some filter function, some short sequence, and find that the composition law is violated. So that's what I think. I do have solutions for some exercises at the end of the book, in the appendix section. So in certain cases, when I found that it's difficult to understand if it's true or not what I'm saying, then I would write down the solution. I didn't always do that, but essentially, anyway. Yeah. So yeah, the composition law, and the composition law is probably going to be violated.
Right. So it occurs to me that maybe the way to phrase Pete's law is as a sort of anti-identity law, which says that if there is any case where the filter function returns false, then the filtered thing is not equal to the original thing.
Okay, well, this would be violated by perfectly harmless examples like a constant functor, a collection that's always empty. So filtering it remains empty.
Right.
So
But
that would violate the requirement that it changes when something is false. There's never anything that's false.
Right. So yes. So that rule does not apply to an
no, but you don't know, right? So you say you give it a predicate that's identically false, and it should not return the same sequence, but the same collection.
Right. That is not how it's phrased. It says if there is some if some call to the filtering function on this thing returns false. So there must be at least one call to the function, and it must return.
So it can't be empty because there has to be at least exist one thing for which it's false.
Right. Yeah. Well, I don't know how to formulate that kind of law.
I'm not sure how to formulate that either, but that seems like it might be Pete's intuition.
Yeah. I tried to do some stuff with like composing it with not P, but that doesn't really work.
Right. But it does seem, yeah, as we get into these more complicated structures, as if there might be a lot of sort of different bells and whistles that you might, different variations on the structure that you might be interested in.
So anyway, I need to drop off now. I'll have to feed her. So I'll say goodbye for now.
Okay.
Cheers.
Bye, you
All
guys.
right.
Oh.
Bye.
All right, so let's see, are we back at the exercises? 9.1.5.3.
I'm still hoping to find an example for 9152. We haven't quite resolved, but we can do that separate. We can do that in Slack.
Right, so yes, okay, suppose there is a sequence where number of which P of Y equals false. So you have to throw out everything if there is an odd number of falses. Well, in the composition law, if you break the sequence into two pieces, where you have one piece with an even number of falses and one with an odd number of falses, then you are required to throw everything out. But in that case, the total number of falses was odd to begin with. So
Wait a minute, what are you saying? The composition law doesn't talk about dealing with two different segments independently. Is that what you're saying?
Yeah, you can't do that.
It's more like if we
right.
had I'm trying to think in terms of if we had a pre-filter that threw out the second element or something like that, but left the rest, then if we apply that if we don't apply it and apply our filter, then it might return true because there'd be an even number of things and then it returns true. But if we apply this other filter first, it would throw out one and then when you apply the filter, it would give you a different result.
Yeah, the problem with that is
then if you then put the two filters together, what happens? If you put the two predicates.
Filter throws out one element, then it's required to throw out all the elements because one is an odd number. So,
Well, I could write a filter that just throws out the third one.
yeah, but
I
then,
think according to his laws,
then
and
you're
everything
not-
else it leaves.
Then you are not. Then you're not doing what the problem wants you to do, which is just to apply even filter to the.
But even filter has to satisfy the composition law. That's what I'm
Yeah, it
saying.
does have to satisfy the composition laws, but which is why I'm still looking for the place where the composition law is violated.
Yeah, I'd have to work it through.
The composition law, it's not only gives us idempotence, but it gives us commutativity as well. I didn't realize that.
So,
Oh, that's interesting.
right, commutativity of filtering functions.
Yeah, because and is commutative.
Yes,
The and of your conditions doesn't matter what order you do it in. That means it doesn't matter which order you filter
yeah.
two things in. I don't know if that's relevant. I just suddenly.
But anytime you filter by anytime you filter and throw out an even number of things, you're going to do a sort of vanilla filter where you retain everything else. Value is kept in the sequence if there's an even number of total elements.
So even filter, like if P returns false, 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 true, then it will keep that last true, right?
Yes.
But if I precompose it with a filter that throws out the third one, then you'd get true, true, true. I mean, false, 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 true, which then it would throw out because it's not an even number. But if you compose the two predicates, don't you get P back because P already returned false for the third one?
Right. So
You know what I'm
here's
saying?
the violation. If you apply two separate filters, each of which throws out one element, the first one is going to throw out everything because it's an odd number of elements. But the composition law and the constraint in the program, or the constraint in the problem that says that you have to retain elements for which P of X equals true, you won't be able to retain those elements if you obey the composition law and the constraint that you throw out everything if you have an odd number of falses. You can't have two consecutive filters, each of which would throw out an odd number if because the AND of them would throw out an even number, meaning you'd have to keep everything for which P returned true. But as soon as you
so your type has 3 values, and the first filter rejects one of them, and the second filter rejects another of them.
right.
Does that
So
work?
yes, say it's 1, 2, 3, and the first filter returns false for 1, the second returns false for 2. So the composition law says that you have to reject both 1 and 2, which is an even number, which means you must retain 3. But the first filter will have given you an empty result because you had an odd number for which it returned false,
Right.
because it only rejected 1. So yes, it cannot obey the specification of the problem and also the composition law.
The composition of the filters throws everything away, whereas
Yeah.
the filter of the conjunction, the filter on the conjunction throws away everything except 1.
Yes.
Okay, I like it. Thank you.
All right. That
It
took
might
us-
help.
So we're
it might help
saying
to draw this.
it's not lawful because it doesn't satisfy composition in
Right.
certain cases.
Right.
Okay.
If possible, implement the filter function or a filterable type class.
Checking is optional.
With respect to the type parameter A. Okay, so for A, yeah, I think we can filter that. Because you can just have user 1 and user 2 be set to none if the condition fails on A. But you cannot do it for the second one because of the Z field. There's no way to get rid of Z if the condition fails. Does that sound right?
Say it again. I'm having trouble kind of grasping how. So we're filtering with respect to the type parameter A. So our predicates on the A
Yeah, it's A to Boolean.
aspect of this thing.
Right. So you can filter the first case class Q, but not R. And the reason is that R has a naked A. And there's no
Oh, wait,
way-
are we doing A or B? I'm sorry.
Well, both actually. So,
Oh, okay,
so A is yes, B is no.
I see.
C cannot be filtered because you have the product of all those A's and there's no thing to replace those with if the filter function returns false. D, yes, you can filter that. I think, yes, because you can always return 1 if the filter function returns false.
Hmm.
One of my larger questions about this, yeah, I'm still not following all this stuff, but that's okay. We are trying to head toward a way of identifying which type constructors are filterable and which are not.
Yes.
Basically an algorithm by which you could look at the expression that defines the functor, the type constructor, and say whether it's filterable or not. But I don't remember that like such an algorithm was ever articulated. It looks like you have an intuitive version in your mind.
Right.
Which I probably would have too if I'd done the exercises, but we didn't ever state something like that, did we?
Right. So I think it's section 9.2.4 where Sergey starts to go through the various possible forms of functors to determine which ones you can do filtering on. So yeah, he does the usual thing where he looks at you know, constants and products and sums and exponential types and you know, the whole set of things that you can use to build up a functor.
Product. So product is okay. Gosh, this is long. Object functors. So are you saying there's an algorithm that arises by reading this section?
Yes.
Cool.
For certain, yeah, for certain constructions, as long as it follows.
Sometimes. And do we know that for the other
Yeah.
constructions, it fails to be filterable?
It's a good question.
Right. Well, for the identity functor, it fails to be filterable. So if you try to do a filter on A, and you're doing it on just the type A, there's nothing to replace your A with if the filter function returns false. There's no way to
Right.
throw it.
Right.
And so that is not filterable.
So this is the naked A criterion that you were
Naked
mentioning
A.
earlier.
And so also a product in which A is one of the factors, that won't be filterable because in order to reconstruct the product, you have to have an A. And if you've thrown out the A, what are you going to do? So this product in C case C here, where you have 3 A's. You can think, well, if you throw out one of the A's, maybe you can replace it with another of the A's or something. But if the filter function returns false for all 3, then you don't have any A's anymore.
Well, A could be a unit.
It could be, but only if the type A is this is for any type A. So it could also be it could also be
Nat or something.
or string or
Well, I guess nat is okay because you can always replace it by 0 or something, but
yes.
Well, anyway, if there were such an algorithm, it would be nice to see it in here, even if it's only partial.
Right, it's in there.
Okay,
Yeah, you just have to keep reading.
very good. I was skimming.
well, we're almost out of time. Do we want to take a
no.
time for next week or next time?
Next time, 2 weeks from today is the 8th of April. Is that good for people? Bad for people?
It's okay for me, I guess.
All right.
That's okay for me.
Okay, so I guess we will pick up here with the exercises 9.1.5.4. And okay.
I wonder if we should maybe, I mean, it's going to take a long time if we keep going through all this stuff. Maybe we should do the chapter 10.
We could, although even more exciting might be, well, I mean, Hugh has made it clear
Or do
that
the further developments and then 10.
yeah, I think Hugh has made it clear that we should at least skim section 9.2.4, which tells us which forms of things you can have a filterable for. But the further developments is interesting. It is particularly interesting in this chapter, where Sergei is talking about the various forms that naturality laws can take. That's, I suspect, something that will come up again later in the book. So, yeah, we probably don't have to read the section that describes which forms of functors are filterable in any great detail, because it pretty much matches your intuition. But yeah, the further developments section is definitely worth a look. So yeah, and then we can read into chapter 10 if anybody is sufficiently motivated. And I will try to work on my Agda example and see if I can get any farther on that. So does that sound good?
For me, it's very good.
Yeah.
Thank you.
Okay.
Yeah.
All right. Well, see you all in 2 weeks.
Oh,
Were any of the previous chapters covered in the past?
Yes, we've been working through this book from the beginning. So usually
The
it
recordings are there somewhere.
Yes, the recordings should all be there. It usually takes us more than one meeting to cover a chapter, as you can see. The material is pretty dense, and it brings up a lot of other questions that we get sidetracked on. And so, yeah, it's been pretty good as far as stimulating discussion.
But if you want to learn functional programming, like in Scala, I think there's like a book or even a video series on that might be more useful.
Right. This material kind of assumes that you know something about functional programming and are interested in understanding, not just how it works, but why it works.
Yeah, this is about the mathematics kind of behind it.
Yeah. So
Anyway, that's my opinion. All
yeah.
right.
So 2 weeks.
All right.
Sounds good.
Okay.
Thank you.
Ciao. Thank you.